Welcome to this lecture of calculus. In this lecture, we shall study the Rolle's theorem. We shall take up its proof and then we will also take up some examples. Now, first of all, we shall state what we have in the Rolle's theorem. The Rolle's theorem states that if we have a function defined on a closed interval a, b, such that the function is continuous on the closed interval a, comma b, the function is differentiable on the open interval a, comma b, and f of a is equal to f of b. That means at the endpoints of the interval, the functional values are identical. Then the theorem states that there is at least one point c in the open interval a, comma b at which the derivative of the function is equal to 0. So therefore we have three conditions for the conclusion of the Rolle's theorem. We have the first condition that the function should be continuous on the whole interval, including the points a, comma b. The function should be differentiable on the whole interval, but except possibly the extreme points of the interval a, comma b, and the functional values at the extreme points should be equal. Then we have the conclusion in the theorem that there is at least one point in the interval a, comma b where the derivative of the function is equal to 0. Now let's take up the proof of this theorem first, and then we shall also see its geometrical interpretation, and then we shall take up some examples. Now what we are given f of x is continuous on the closed interval a, comma b. Therefore, by the extreme value theorem, thus by extreme value theorem, the function f of x attains its extreme values. This attains the absolute maximum and the absolute minimum on the closed interval a, comma b. Now here we have two cases to consider. The first case is when these two extreme values, that means the absolute maximum and the absolute minimum values are equal, and the second case is the absolute maximum and the absolute minimum values are not equal. So therefore we have case number 1, the maximum and minimum values are equal. Now this is a case when we have a function whose maximum value equals its minimum value. That means such a function must be a constant function. So then f of x is a constant function. Therefore f dash of x is equal to 0 for all x belongs to the interval a, comma b. So therefore in this case the derivative of the function is 0 at every point. So therefore there is a point in the interval open interval a, comma b such that f dash of c is equal to 0. So in fact this is true for every point in the interval a, comma b when the function is a constant function. Now here we shall try to understand properly why such a function has to be a constant function. Let's take up one simple example here. Suppose if we have a function which is like a function like this. If we have like this is from this graph we can see this is the point at which the function attains the maximum value, and this is a point where the function attains the minimum value. Now in this graph we can see that the maximum value is not equal to the minimum value. So maximum value is this height and minimum value is something negative, this height. But now if we have a function that the maximum value suppose is attained at suppose this point, say suppose x0, and then we have another point suppose x1 at which the minimum value is attained but maximum and the minimum values are same. So if these two values are same where the function attains the minimum and the maximum value, that means the function neither goes above from this point nor it goes below this point where it attains the maximum and the minimum value. So therefore the graph of the function simply behaves like this. So it's a straight line parallel to x-axis. So in this case the function has to be a constant function. Now let's take up the second case. So this is case number 2. The maximum values and the minimum values are different. Maximum value is not equal to the minimum value. Now in this case we have, since f of a is equal to f of b, therefore either the maximum or the minimum value must be attained at some interior point. Now why we have a case like this when f of a is equal to f of b and the maximum and the minimum values are equal? Now in this case we are assuming the maximum value is not equal to the minimum value. And in the statement, we are given that f of a is equal to f of b. Now, assuming that suppose if f of a is the minimum value, then since f of a is equal to f of b, therefore f of b cannot be the maximum value because maximum and minimum are not equal. And similarly, if f of a happens to be the minimum value, then the same cannot be the maximum value because we have minimum and maximum values are different. So therefore, the case when the functional values at the endpoints are equal and the minimum and the maximum values are not same, therefore, if f of a is minimum, then the maximum will be attained at some different point, which is different from a and b. So that will be necessarily, obviously, a point which is the interior point of the open interval a comma b. And similarly, if f of a is the maximum value, then the minimum will be attained at some interior point. But we already have that at an interior point, if the extreme value is obtained, then the derivative at that point must be equal to 0. So, but if an extreme value is attained at an interior point, say C, then derivative at C must be equal to 0. That is, f dash of C is equal to 0 at such C which belongs to the open interval a comma b. Therefore, we have proved the existence of a point C in the open interval a comma b at which the derivative of the function is equal to 0. So this completes the proof of the Rolle's theorem. Now let's take its geometrical interpretation and then we shall take up an example. Let's consider a function like this. So suppose we take a function like this, and suppose this is the point A, and suppose this is the point B. Then in the Rolle's theorem, we have the functional values at the point A comma B are equal. So we can take the point B like this. So we take the function like this. So this is the functional value at A and functional value at B is equal to equal. So therefore, in this case, f of A is equal to f of B. Then this is a continuous function on the closed interval a comma b, differentiable in the open interval a comma b, and also f of a is equal to f of b. So then here we can obviously find out this point at which the derivative, at which the tangent to the graph is parallel to x-axis, and similarly this is the point at which the tangent to the graph is parallel to x-axis. So this means that we have, this is a point, suppose this is a point C1 and this is a point C2, such that this f dash of C1 is equal to 0 and similarly f dash of C2 is equal to 0. Therefore, the Rolle's theorem geometrically states that if we have a function which is differentiable on the open interval a comma b, continuous on the closed interval a comma b, and f of a is equal to f of b, then there is at least one point C belonging to the open interval a comma b at which the tangent is parallel to x-axis. So thus Rolle's theorem gives the existence of a point C belonging to the open interval a comma b such that a tangent is parallel to x-axis at this point C. So this is the geometrical interpretation. Now let's take up an example. Verify Rolle's theorem for f of x is equal to x square minus 4x plus 3 on the interval 1 comma 3. Then the solution is, so we have f of x is equal to x square minus 4x plus 3. This is defined on the interval 1 comma 3. Then the first condition is f of x is continuous on the interval 1 comma 3. Second, because it's a polynomial function and every polynomial function is also differentiable, f of x is differentiable also on the open interval 1 comma 3. The third condition is, let's compute the value f of 1. This is equal to 1 minus 4 plus 3, which is equal to 0. And f of 3, this is also equal to 0. So therefore, f of 1 is equal to f of 3. So hence by Rolle's theorem, there exists C belonging to the open interval 1 comma 3 such that f dash of c is equal to 0. Now first let's compute what is f dash of x. So now f dash of x, now we can take the derivative of the given polynomial, and the derivative is 2x minus 4. So therefore f dash of c equal to 0 gives 2c minus 4 is equal to 0, and this gives c is equal to 4 divided by 2. So this implies c is equal to 2, and we can clearly see that the point c equal to 2 belongs to the interval 1 comma 3, and this c equal to 2 belongs to the interval 1 comma. Thus the Rolle's theorem has given us a point c equal to 2 in the open interval 1 comma 3 at which the derivative of the function is equal to 0.